work and energy, impulse and momentum, and then appendix. Appendix is going to store all the stuff that is ancillary to the main topics, but these were the main topics. And although we have 7 units, many of the units repeat. So like all of rotational motion repeats Newton's laws, work and energy, impulse and momentum. So in our first unit is kinematics. So if we take those two out, we're left with what I would say 2 ancillary units. And one of them was gravity and orbits. And one of them was simple harmonic motion, which are ultimately just extensions to Newton's laws, work and energy, impulse and momentum. So I want to kind of talk to you about when you're looking at a problem, what's the problem likely about? And can you always fit it into one of these 3 categories? And because one of the things you have to start coming to grips with is that you're going to be faced with a problem. And although we have different styles of problems, you have to know how to attack the problem. Like, what is the best course of action for any one of the problems? So let's start with what these really are about. And ultimately, let's remember that the ancillary material usually comes from one of these categories, not the reverse. For example, one of the ancillary materials is kinematics. Kinematics was an introduction to vocabulary, and at the same time did things like V equals AT plus V naught, or X equals 1/2 AT squared plus V naught times T. We called those motion equations, but they were very specific. They're Galileo's motion equations, and they only worked when acceleration was constant. So there's a very small subset. What it was actually supposed to be doing was teaching you the vocabulary of physics. The fact that for the most part, the most important measurement in physics is acceleration, because it represents something that is changing about the object. So when we ultimately think about all of physics, accelerations are important because velocities merely mean something had already happened to the object. That's what got it into motion. But when something accelerates, there's something acting on it actively. Something's happening. And any acceleration means there's something out there pushing your object around. Accelerations can't happen without forces. Now, the rest of these topics are about trying to deal with that idea and work within that concept. So let's start with Newton's laws. There's 2 parts to Newton's laws. Things that are static, where net force and net torque equals 0. And there's things that are dynamic, where net force equals ma, or net torque equals I alpha. I'll remind you that the only thing that Newton's laws can actually do, and the way we phrased it, or the way we framed it, is they can tell you the size of an acceleration, or they can tell you the size of an individual force or torque. That's what the Newton's laws can do. They can tell you the size of an acceleration, or they can tell you the size of an individual force or torque. That's all that Newton's laws can do. Now, once you have a force, or once you have the acceleration, you could then apply that to kinematics, or you could apply that somewhere else. But all Newton's laws can do is tell you the size of a force or the size of a torque. Now, we have different kinds of accelerations, and it's important that you remember there are different kinds of accelerations, which is why again, ancillary, the appendix. There's tangential accelerations. These change speed. And there's centripetal accelerations, which change direction. Again, that's an appendix. Forces can tell you an acceleration. What that acceleration does depends on whether it's in the direction of motion or whether it's perpendicular to the direction of motion. Remember, these are in the direction of motion, and these are perpendicular to the direction of motion. You can have an acceleration that does both, speeds the object up and changes its direction. It happens to you guys all the time. You're making a left turn, you hit the turn too fast, you slam on the brakes and turn the wheel. 2 accelerations, one to change the speed, one to change the direction. It is important to note that ones that change direction are based on speed. Right, centripetal acceleration is a substitution, it's based on speed. But I still say force problems are generally about acceleration and force. Now, force problems deal with other things too. A problem that has friction in it is very likely to require you to deal with force. Very likely. So if the problem brings up a coefficient of friction, you're probably going to be doing a force problem. But I also want to remind you that force problems represent generally the most difficult way of solving a problem. They require the most analysis and a lot of work generally to deal with them. Be careful of the words system versus. If you're asked about Newton's laws relative to a system, you're applying it to all the objects in the system. But if you're only asked about an object, then you focus on the set of rules we did. The rules we did were about an object. To deal with the system, you had to apply the rules to every object in the system. That created internal forces and external forces. Forces in the system obeyed Newton's third law. They were equal and opposite. But the biggest takeaway about Newton's laws is the concept of inertia. The effectiveness of a force depends on inertia, whether that be mass or moment of inertia. So when do I use Newton's laws? If they ask for a force, you're likely going to use Newton's laws. Now, work and energy, I'll remind you, starting with work, work is the method to change something's energy. In order to do work, you have to apply a force in the direction of motion or against the direction of motion. In the direction of motion, increases its kinetic energy. Against the direction of motion, decreases its kinetic energy. With work, we're either increasing kinetic energy, decreasing kinetic energy, increasing potential energy, decreasing potential energy. We're doing something, but we're trying to change the energy of the system. If there's unbalanced forces, then work directly changes the kinetic energy. And I know I'm speaking in equations, but they're more compact and efficient. So if this, then that. So you should always remember, if they ask for how much work is done, the easiest way to find it is changing kinetic energy. Always will be. If there is no external, let me say this different. If you have an isolated system, I'm saying it very specifically, I know it's a lot of words, but if you have an isolated system with no external non-conservative forces, friction, air resistance, then the sum of all the forms of energy that you know is a constant. There can be an external force. Gravity is an external force, but it's a conservative force. It stores potential energy. There could be an external force like a spring, but that's a conservative force. So we don't say that there's no external forces. We merely say there's no non-conservative forces, something that takes away the energy. And the only things that take away energy tend to be friction or air resistance. So if there's no friction or air resistance, then you want to look at conservation of energy. Yeah.
So doesn't that mean the same thing when you say the energy is constant or it's conserved?
Yes.
It's the same thing?
It's the same thing. I just couldn't fit the word conserve there. What I mean is that it equals the same number. So you could put all the energies before something happens equals all the energies after something happens. Does that make sense? All right. Now, when would you use work in energy problems? Work is really good at dealing with velocity. Work is really good in dealing with problems that have changes in height. And be careful, because this one is one of those ones that people tend to think, oh, I see this, so it has to be energy. But springs often are problems that deal with energy. So if there's a spring, but be careful. Springs also show up with forces too. We saw that on yesterday's FRQ, right? The spring pulling on the mass as it was going in the circle. So don't assume a spring automatically means energy. Okay? Springs store energy, but they also apply forces. Which brings me to another appendix item, Hooke's law. So when you see an object center of mass change height, you should think work and energy. When you see an object that's rolling down a ramp, that's probably conservation of energy problem. Hits a spring and compresses it, probably a conservation of energy problem. Especially if the ramp isn't straight but curved. Can't use Newton's laws on it, probably a conservation of energy problem. Now, I'm going to slide this up because there's more to this, and I know you might be running out of space, but I have to write big and chunky. There are things that work's not particularly good at. Time. Doesn't show up very much. So solving for time is tough. But be careful. Power has time in it. It's work over time. So the only time you can deal with time in an energy problem is if they ask or give you power. So be aware of that. But also, not good at finding accelerations. And not particularly good at giving you individual forces unless you know how much work is being done. I mean, force is in the work equation, but it's not really equipped for this to be worked backwards. You can do it, but it's not really equipped the same way. We generally think of work problems as problems that deal with energy. Remind you that any change in momentum is an impulse. An impulse only occurs if there's an unbalanced force. Only occurs if there's an unbalanced force. Now, I'm going to put something out in front of you because it's a different way of thinking of Newton's second law. But impulse is a restatement of Newton's second law. Now, if I just divide both sides by t, we get net force equals. So this is ma. Just keep that in mind. It's buried in there. So this version of impulse separates out Newton's laws a little bit. If an object's velocity changes, that means there had to be an impulse applied to the object. And don't forget that all of these have an angular component too. All of them do. In fact, what I was neglecting, I should have put this down, is don't forget that torque is like a force, but for things that twist, and you have to kind of do a little extra work to find the torque. But what is really the crux of momentum is dealing with when one object interacts with another. Collisions were a big part of our discussion about momentum, because momentum is a conserved quantity in all collisions. Whenever one object contacts another, momentum is conserved. This is due to Newton's third law. We proved it with Newton's third law, that for every impulse, there's an equal and opposite impulse. So when you add up all the momentums of the objects before a collision, it has to equal all of the momentums of the objects after the collision. But momentum is different than energy because it deals with direction. Energy doesn't deal with direction in any way. If energy gets bigger or energy gets smaller, it can be positive or negative, but it doesn't tell you what direction the object's going. But momentum is tightly integrated with direction. But remember too, a collision is just the instantaneous moment before contact and the instantaneous moment after contact. That's always a collision. And collisions don't have to be one object hitting another. It could be one object landing on top of another. So collision is any time there's going to be contact between two objects. That's going to be a collision. And that's when we tend to use momentum the most. So you can usually identify a collision question because it's going to involve two or more objects and there's contact between them. During the time of contact, they're in contact for the same amount of time, experiencing equal and opposite forces. But also be aware that momentum conservation for angular momentum can be about one object changing its shape. Right? Mr. Shelton standing on the spinning thing, pulling his arms in, changes his moment of inertia and changes the velocity, but the angular momentum stayed the same. This isn't a collision question, but it's still a conservation of momentum question. And also, don't forget the kid running towards the merry-go-round and then giving its angular momentum to the merry-go-round. The idea that there is a point mass angular momentum. Now, there's a lot of appendices, things that don't fit into other categories. The biggest one, projectiles. We did a subset of projectiles. All of our projectiles were a constant acceleration in one direction, no acceleration in another direction. But projectiles are just two-dimensional motion. You could have two different accelerations, one in the x direction and one in the y direction. There's no reason you can't. It's just a system in which you break your problem up into a horizontal portion and a vertical portion. The biggest thing about projectile problems is that your object is experiencing generally motion in two different dimensions, but the time it takes to move in one direction is equal to the time it takes to move in the other. We did vertical, horizontal, where the horizontal didn't change. That was most of what we did.